SwayamPrabha.
Welcome. So, in the last class, we have defined kernelization algorithms and we have seen easy kernel, a quadratic kernel for vertex cover problem, and we have also seen that kernelization algorithm is equivalent to FPT algorithms. That means we have an FPT algorithms if and only if there exists a kernelization algorithm, if there exists at least one algorithm for the problem. So, today we will see more non-trivial kernelization algorithm for vertex cover, which is based on linear programming. So, kernelization algorithm for vertex cover based on linear programming. So, let us recall what is the linear program for vertex cover. So, linear program relaxation for vertex cover. So, let us consider the unweighted vertex cover. So, for every vertex we have a variable v and we want to minimize summation xv v in v. Okay, and what are the constraints? Subject to for each edge e equal to u comma v, we have this edge must be covered, that means xu plus xv, this should be greater than equal to 1, and for each edge this in E, and for each vertex v in v, xv this is greater than equal to 0. Okay. So, now recall that we have proved that every extreme point of this linear program is half integral. Recall, every extreme point of the above linear program polytope is half integral. In particular, the extreme every extreme optimal points, optimal solutions are also half integral. So, the first step is to compute this extreme, compute an optimal solution. So, reduction rule, what is the, let us write the reduction rule. So, we first apply those reduction rules also. This is an additional reduction rule, which is, so this reduction rule, we have 0, 1, 2 before, now we have reduction rule 3. What does this reduction rule say? That solve the linear program so first we apply reduction rule 0, 1 and 2 as long as we can, and then we apply reduction rule 3. Solve the linear program. Let xv, x star v, v in v be an extreme optimal solution of the vertex covered LP. Then what we do is that means what? That means xv is a half integral, and we pick all the vertices which are, so define these sets V1 is all those vertices such that x star V is 1, V0 is all the vertices in V such that x star V is 0 and V half is V in V such that x star V is half. So, reduction rule deletes all vertices in V0, picks all vertices in V1 and returns the induced graph on V half. See, picks all vertices in V1 adjust the budget appropriately. That means new k prime is k minus size of V1. Okay. Then it deletes all vertices in V0 and return the induced graph on V half. It all does this if LP opt, the optimal value of LP is less than equal to K. If LP opt is greater than K, then the size of the minimum vertex cover is at least LP opt. LP opt is a lower bound. This we have seen in design of approximation algorithms many times, because the vertex cover problem is basically an integer linear program and we are doing linear programming relaxation. So hence the LP opt is a lower bound on the opt. So if LP opt is greater than equal to K, then clearly there is no vertex cover of size at most K. If LP opt is greater than K, then clearly there is no vertex cover of size at most K. Hence, the instance is a no instance. In this case, the algorithm, the kernelization algorithm, simply outputs a dummy no instance. Okay, but now why if LP opt is less than equal to K, whatever the algorithm is doing, why it is an equivalent instance, that is not clear. Of course, because the solution is half integral, all the vertices for every vertex V, x star of V will be either 0, 1 and half. So this part is clear that V is union of V1, V0 and V half. That part is clear. This is since x star V, V in V is half integral. Okay, but why we are deleting V0 and picking all vertices in V1 part of solution? Why there must exist a minimum vertex cover which is contained in V1 union V half? That's not clear and that needs a separate proof. So that is our next theorem. It is by Nimhauser and Trotter. Okay, it says that there exists at least one minimum vertex cover which contains V1 and is contained in V1 union V half. So, there is a minimum vertex covered S of the input instance such that S is a subset of V1 union V half and is contained in V1. Okay. So, proof. So, let A star subset of V be a minimum vertex covered of G. So, what you do is that from V from A star you remove all vertices in V0 and pick all vertices in V1. So, define S equal to A star minus V0 union V1. Claim S is also a vertex covered. Okay. Why? This is so because this is proof. Since every vertex has an edge and at least one edge, because there is no isolated vertex, and because those reduction rules 0, 1 and 2 has been applied, and since for each edge E equal to u comma v in E, we have xu plus xv greater than equal to 1. So, if a vertex u belongs to v0, that means xu equal to 0, then xv must be equal to 1. So, since this, then if u belongs to v0, then v belongs to v1, that is every neighbor of v0 is a vertex in v1. That means here is v0. Now, there are some edges. First, see that v0 must be an independent set. Also, v0 must be an independent set. There cannot be an edge like this, because then both of its endpoints, this value is 0, and that means there for that edge this constraint is not satisfied. So, there cannot be an edge like this within v0. V0 must be an independent set. Moreover, all the neighbors of v0, this must be in v1. if this is the neighbor of V0, this must contained in V1. It cannot even be in V half, because if it is in V half, then also it is not. These edges, the constraint for these edges are not satisfied. Okay. Now, what are the edges? Where are the edges? Of course, the edges within V1 are satisfied, because all the edges, we have picked entire V1, and here is V half. All the edges within V half are satisfied, all the edges across V1 and V half are satisfied, and all the edges between V0 and V1 are also satisfied. And of course, there is no edge between V0 and V half, there is no such edge. Hence, S is a vertex cover. It covers every edge. S is a vertex cover of the input instance. This proves the claim. Moreover, we have S is contained in V1 union V half. Okay, it contains all vertices in V1 and it does not contain any vertex of V0. So, and this is a superset of V1. It contains all vertices of V1. So, S has all these properties that this set, the minimum vertex cover we are looking for. S has all these properties. It is a vertex cover. Next, we claim. Next, we prove that S is a minimum vertex cover. Okay, for that we have a minimum vertex cover, namely A star. A star is a minimum vertex cover, and what is cardinality of S minus cardinality of A star? We need to show that this is less than or equal to 0. So, what is this? So, this is from S. What are the vertices which are in S but not in A star? This is the vertices in V1 minus S. V1 minus S star. So, these are the vertices which are in S but not in S star. Minus, now there are some vertices which are in S star but not in S, which are these are V0 intersection S star, because we have removed all the vertices in V0. This is to show that this is less than or equal to 0. This is to show. That is to show that cardinality V1 minus S star, this is greater than or equal to cardinality V0 intersection S star. For that, let us define epsilon equal to minimum of mod of x star V minus half, such that V is in V0 union V1, make it half of this. For this, we now decrease the fractional values from here and increase the fractional values from there. We will construct another solution and we will show that if this is not the case, if this inequality does not hold, then we have a solution of value less than the solution for A star, so which is less than LP opt. Okay, so define another solution YV V in V as follows. Okay, YV is XV minus epsilon if V is in V1 minus A star. This is XV plus epsilon if V is in V0 intersection A star and XV otherwise. Okay, so now what is summation YV V in V? Just a minute, we need to show that this is less than equal to 0, that means this is less than equal to 0. Okay, and it's a proof by contradiction. So for contradiction, let us assume that mod of V1 minus A star is strictly more than V0 intersection A star. Now under this assumption, we will show that YV has less value, YV is less than. Now all the variables in V minus A star, their value has dropped, and all the variables in V intersection A star, their value has increased. So more number of variables values have dropped and less number of variables have increased. So sum of YV is less than sum of XV. Then all we need to show that YV is indeed a feasible solution, which can be shown by easy case analysis. So by easy case analysis, it can be shown that YV V in V is a feasible solution of the LP is X star V, but this contradicts that X star V is an optimal solution. But this contradicts that X star V in V is an optimal solution. Okay, hence we have we have this, that size of V1 minus A star, this is less than equal to size of V0 intersection A star, and thus S is a minimum vertex covered. Okay. Now, what is the size of the kernel? Size of the cardinality V0 union V half is less than equal to not V0 V1. So, this is the output of the algorithm, output of the kernelization algorithm, summation V in V1 union V half twice X star V, but this is then this is twice LP opt, but LP opt must be at most k, this is less than equal to 2k. So, size of kernel, the kernel contains the output instance which is called kernel, contains at most 2k vertices, which is an improvement from our quadratic kernel which contain at most k square vertices, because it contains at most k square edges. So, okay, we will stop here today. Okay.